Section 6.12. Expressing the equilibrium constant in terms of mole fraction and the molarity. So first, let's look at this equilibrium constant of pressures. We use the pressures of the products and reactants. Make sure you divide each pressure by P0 to compare the pressure with the standard state, because again, the standard state is used as the reference. And then we need to put the coefficients over here as the power of this P over P0. This is K sub P at equilibrium. Now, if we know the total pressure is this P in bold font, then P sub X is the mole fraction of X times P. P sub Y is the mole fraction of Y times P. P sub A is the mole fraction of A times the total pressure of the mixture. So we can replace every single partial pressure with its mole fraction times the total pressure P in bold font. And then we can actually take this P over P0 out of this square parenthesis. So right now it's here. And then P over P0 to the power of nu X plus nu Y minus nu A minus nu B. So it's right here. What's left? The left is the mole fractions. Again, the mole fractions of the products on top, the mole fractions of the reactants on the bottom. Still, we have those coefficients, nu X, nu Y, nu A, and nu B. So this part is called the equilibrium constant of mole fractions. So now you can see this equilibrium constant of pressures is equal to the mole fraction, the equilibrium constant of mole fractions times this, the total pressure over P0 to the power of delta nu. Delta nu is the coefficients of the products minus the coefficients of the reactants. I want to emphasize this delta nu only count the coefficients of the gases. If you see solids and liquids in a chemical reaction, do not take their coefficients into account. This delta nu is referring to those gases. Now let's look at another equilibrium constant. The equilibrium constant of molarity, concentration, over here. So first, we need to look at the relation between the concentration and the pressure. The concentration of a gas, C sub I, species I, is simply N over V, the number of moles over volume. And if we assume the gas is an ideal gas, N over V is simply P over RT. For species I, it's partial pressure of I over RT. Therefore, we have this relation, P sub I is equal to C sub I times RT. The partial pressure of species I is equal to the molarity of I times RT. They just differ by a constant RT. Now, let's transfer this P sub I over P0. P sub I is CIRT over P0. And then we multiply this top by C0 and the bottom by C0. So you see C0 here, C0 here. And then Ci over C0. That's the concentration of species I compared to the standard state in concentration. Again, C sub I over C0 is the concentration of species I compared to the standard 1 molar concentration. And then we have this C0 times RT over P0. This C0 is 1 molar, R is the ideal constant, T is the reaction temperature, P0 is 1 bar. So now we can plug in this formula in the expression of the equilibrium constant of pressures. This is complicated enough, but we need to make it more complicated by plugging this in each of the 4 terms. 2 on the top, they are the products. 2 on the bottom, they are the reactants. So over here, and then we put all those concentrations together to get this equilibrium constant of concentrations. So this is K sub C, the equilibrium constant of concentrations or equilibrium constant of molarity. And then we see there's a common factor, C naught RT over P naught, C naught RT over P naught, here and here. So it appears in 4 different places. So we put them together, and then we have nu x plus nu y minus nu a minus nu b here. Alright, so now we can see K sub P is equal to K sub C, the equilibrium constant of molarity, times this C naught times RT over P naught to the power of delta nu. K sub P is unitless. K sub C is also unitless. So this must be also unitless. If we know what the temperature is, we can compute this part. If the temperature is the room temperature, we'll just look at C naught times RT over P naught. C naught is 1 mole per liter or 1 molar, and then we have R here, and we have temperature, we have pressure. P naught is 1 bar. 1 bar is 10 to the power of 5 pascals. 1 liter is 10 to the power of -3 cubic meter. So after you do the conversion, you'll see the result is roughly 25. So really Kp equals Kc times 25 to the power of delta nu. And again, this nu is referring to the coefficients of the gases in the reaction. If you see solids and liquids, they don't count. Again, because we used PV equals nRT over here, you never use PV equals nRT for a solid or a liquid.